256 Research Methodology 11 Analysis of Variance and Company Variance Analysis of Variance ANOVA Analysis of variance, abbreviated as ANOVA, is an extremely useful technique concerning researches in the fields of economics, biology, education, psychology, sociology, business, industry and in researches of several other disciplines. This technique is used when multiple sample cases are involved. As stated earlier, the significance of the difference between the means of two samples can be judged through either z-test or the t-test, but the difficulty arises when we happen to examine the significance of the difference amongst more than two sample means at the same time. The ANOVA technique enables us to perform this simultaneous test and as such is considered to be an important tool of analysis in the hands of a researcher. Using this technique, one can draw inferences about whether the samples have been drawn from populations having the same mean. The ANOVA technique is important in the context of all those situations where we want to compare more than two populations, such as in comparing the yield of crop from several varieties of seeds, the gasoline mileage of 4 automobiles, the smoking habits of 5 groups of university students and so on. In such circumstances one generally does not want to consider all possible combinations of two populations at a time, for that would require a great number of tests before we would be able to arrive at a decision. This would also consume lot of time and money, and even then certain relationships may be left unidentified, particularly the interaction effects. Therefore, one quite often utilizes the ANOVA technique and through it investigates the differences among the means of all the populations simultaneously. What is ANOVA? Professor R.A. Fisher was the first man to use the term variance, and, in fact, it was he who developed a very elaborate theory concerning ANOVA, explaining its usefulness in practical field. Variance is an important statistical measure and is described as the mean of the squares of deviations taken from the mean of the given series of data. It is a frequently used measure of variation. Its square root is known as standard deviation, i.e., standard deviation equals variance. Analysis of variance and company variance 257. Later on Professor Snedekor and many others contributed to the development of this technique. ANOVA is essentially a procedure for testing the difference among different groups of data for homogeneity. The essence of ANOVA is that the total amount of variation in a set of data is broken down into two types, that amount which can be attributed to chance and that amount which can be attributed to specified causes. 1. There may be variation between samples and also within sample items. ANOVA consists in splitting the variance for analytical purposes. Hence, it is a method of analyzing the variance to which a response is subject into its various components corresponding to various sources of variation. Through this technique one can explain whether various varieties of seeds or fertilizers or soils differ significantly so that a policy decision could be taken accordingly, concerning a particular variety in the context of agriculture researches. Similarly, the differences in various types of feed prepared for a particular class of animal or various types of drugs manufactured for curing a specific disease may be studied and judged to be significant or not through the application of ANOVA technique. Likewise, a manager of a big concern can analyze the performance of various salesmen of his concern in order to know whether their performances differ significantly. Thus, through ANOVA technique one can, in general, investigate any number of factors which are hypothesized or said to influence the dependent variable. One may as well investigate the differences amongst various categories within each of these factors which may have a large number of possible values. If we take only one factor and investigate the differences amongst its various categories having numerous possible values, we are said to use one-way ANOVA, and in case we investigate two factors at the same time, then we use two-way ANOVA. In a two or more way ANOVA, the interaction, i.e., interrelation between two independent variables, factors, if any, between two independent variables affecting a dependent variable can as well be studied for better decisions. The basic principle of ANOVA. The basic principle of ANOVA is to test for differences among the means of the populations by examining the amount of variation within each of these samples, relative to the amount of variation between the samples. In terms of variation within the given population, it is assumed that the values of Sh differ from the mean of this population only because of random effects, i.e., there are influences on Sh which are unexplainable, whereas in examining differences between populations we assume that the difference between the mean of the JTH population and the grand mean is attributable to what is called a specific factor, or what is technically described as treatment effect. Thus, while using ANOVA, we assume that each of the samples is drawn from a normal population and that each of these populations has the same variance. We also assume that all factors other than the one or more being tested are effectively controlled. This, in other words, means that we assume the absence of many factors that might affect our conclusions concerning the factors to be studied. In short, we have to make two estimates of population variance, viz. one based on between samples variance and the other based on within samples variance. Then the said two estimates of population variance are compared with F-test, wherein we work out F equals estimate of population variance based on between samples variance, estimate of population variance based on within samples variance. 1. Donald L. Harnett and James L. Murphy, Introductory Statistical Analysis, p. 376. 258 Research methodology. This value of F is to be compared to the F limit for given degrees of freedom. If the F value we work out is equal or exceeds the F limit value, to be seen from F tables number 4a and 4b given in appendix, we may say that there are significant differences between the sample means. ANOVA technique, one way, or single factor ANOVA. Under the one-way ANOVA, we consider only one factor and then observe that the reason for said factor to be important is that several possible types of samples can occur within that factor. We then determine if there are differences within that factor. The technique involves the following steps. I. Obtain the mean of each sample, i.e., obtain XXXXK123, when there are k samples. E. Work out the mean of the sample means as follows, XXXXXKK equals plus 123. Know of samples. E. Take the deviations of the sample means from the mean of the sample means and calculate the square of such deviations, which may be multiplied by the number of items in the corresponding sample, and then obtain their total. This is known as the sum of squares for variance between the samples, or SS between. Symbolically, this can be written SSNXXNXXNXXKK between equals 121222 minus FHIK plus FHIK plus minus FHIK. IV. Divide the result of the eth step by the degrees of freedom between the samples to obtain variance or mean square MS between samples. Symbolically, this can be written MSSSK between equals between -1, where K1 represents degrees of freedom d. F. Between samples. V. Obtain the deviations of the values of the sample items for all the samples from corresponding means of the samples and calculate the squares of such deviations and then obtain their total. This total is known as the sum of squares for variance within samples, or SS within. Symbolically, this can be written SSXXXXXXIIKK within equals minus plus n area summation minus plus n area summation minus 1122222 dididi. I equals 1, 2, 3. V. Divide the result of V step by the degrees of freedom within samples to obtain the variance or mean square MS within samples. Symbolically, this can be written. It should be remembered that ANOVA test is always a one-tailed test, since a low calculated value of F from the sample data would mean that the fit of the sample means to the null hypothesis, viz. XXXK12 is a very good fit. Analysis of variance and company variance. 259 mega-Siemens within equals SSNK within, where n, k, represents degrees of freedom within samples, n equals total number of items in all the samples, i.e., n1 plus n2 plus nkk equals number of samples. V. For a check, the sum of squares of deviations for total variance can also be worked out by adding the squares of deviations when the deviations for the individual items in all the samples have been taken from the mean of the sample means. Symbolically, this can be written FSS2 for total variance equals n area summation minus xijxhiki equals 1, 2, 3. J equals 1, 2, 3. This total should be equal to the total of the result of the E and V steps explained above, i.e., SS for total variance equals SS between plus SS within. The degrees of freedom for total variance will be equal to the number of items in all samples minus 1, i.e., N1. The degrees of freedom for between and within must add up to the degrees of freedom for total variance, i.e., N1 equals K1 plus N, K. This fact explains the additive property of the ANOVA technique. V. Finally, F ratio may be worked out as under F ratio equals MS between within. This ratio is used to judge whether the difference among several sample means is significant or is just a matter of sampling fluctuations. For this purpose we look into the table, giving the values of F for given degrees of freedom at different levels of significance. If the worked out value of F, as stated above, is less than the table value of F, the difference is taken as insignificant, i.e., due to chance, and the null hypothesis of no difference between sample means stands. In case the calculated value of F happens to be either equal or more than its table value, the difference is considered as significant, which means the samples could not have come from the same universe, and accordingly the conclusion may be drawn. The higher the calculated value of f is above the table value, the more definite and sure one can be about his conclusions. Setting up analysis of variance table. For the sake of convenience, the information obtained through various steps stated above can be put as under. An extract of table giving f values has been given in appendix at the end of the book in tables 4a and 4b. 260 Research Methodology Table 11.1. Analysis of variance table for one-way ANOVA. There are k samples having in all n items. Source of variation between samples or categories within samples or categories. Total sum of squares SS F2NXX11 minus degrees of freedom D F HIK plus K1 2FNXX plus minus KKHIK 2XXN Airy summation minus plus DI N KI11 DI2 plus minus KXX mean square MS. This is SS divided by D F and is an estimation of variance to be used in F ratio SSF ratio KB Edwin minus 1 SSNK within KI equals 1, 2, 3, F2N Airy summation minus IJXXHIKI equals 1, 2, J equals 1, 2, N minus 1. Shortcut method for one-way ANOVA. MS between within ANOVA can be performed by following the shortcut method, which is usually used in practice since the same happens to be a very convenient method, particularly when means of the samples and/or mean of the sample means happen to be non-integer values. The various steps involved in the shortcut method are as under. I take the total of the values of individual items in all the samples, i.e., work out N Airy summation J I equals 1, 2, 3, J equals 1, 2, 3, and call it as TE. Work out the correction factor as under. Correction factor equals TNBG2. Analysis of variance and company variance. 261 E. Find out the square of all the item values one by one and then take its total. Subtract the correction factor from this total and the result is the sum of squares for total variance. Symbolically, we can write total SSXTNIJ equals minus 2 2BGI equals 1, 2, 3, J equals 1, 2, 3, IV. Obtain the square of each sample total TJ 2 and divide such square value of each sample by the number of items in the concerning sample and take the total of the result thus obtained. Subtract the correction factor from this total and the result is the sum of squares for variance between the samples. Symbolically, we can write SSTNTNJJ between equals minus DIBG2 2J equals 1, 2, 3, where subscript J represents different samples or categories. V. The sum of squares within the samples can be found out by subtracting the result of IV step from the result of each step stated above and can be written as under. SSXTNTNTNIJJJ within equals N Airy summation minus RST UVW minus N Airy summation minus RST UVW 2222BGDIBG equals minus N Airy summation XTNIJJJ 22DI. After doing all this, the table of ANOVA can be set up in the same way as explained earlier. Coding method is furtherance of the shortcut method. This is based on an important property of F ratio that its value does not change if all the n item values are either multiplied or divided by a common figure or if a common figure is either added or subtracted from each of the given n item values. Through this method, big figures are reduced in magnitude by division or subtraction and computation work is simplified without any disturbance on the F ratio. This method should be used specially when given figures are big or otherwise inconvenient. Once the given figures are converted with the help of some common figure, then all the steps of the shortcut method stated above can be adopted for obtaining and interpreting F ratio. Illustration 1. Set up an analysis of variance table for the following per acre production data for 3 varieties of wheat, each grown on 4 plots, and state if the variety differences are significant. 262 Research methodology per acre production data plot of land variety of wheat ABC 1 6552 75433334 Solution. We can solve the problem by the direct method or by shortcut method, but in each case we shall get the same result. We try below both the methods. Solution through direct method. First we calculate the mean of each of these samples. X1673846 equals plus equals X2553745 equals plus equals X3543444 equals plus equals mean of the sample means or XXXXK equals plus 123 equals plus equals 65435. Now we work out SS between and SS within samples. SSNXXNXXNXX between equals 1 2 3 1 2 2 2 3 2 minus FHIK plus minus FHIK plus minus FHIK equals 4, 6 to 5 2 plus 4 5 to 5 2 plus 4 4 to 5 2 equals 4 plus 0 plus 4 equals 8 SSXXXXXXXII within equals minus plus n array summation minus plus n array summation minus 1 1 2 2 2 2 3 3 2 DI I equals 1, 2, 3, 4 equals 6 to 6 2 plus 7 to 6 2 plus 3 to 6 2 plus 8 to 6 2 plus 5 to 5 2 plus 5 to 5 2 plus 3 to 5 2 plus 7 to 5 2 plus 5 to 4 2 plus 4 to 4 2 plus 3 to 4 2 plus 4 to 4 2 equals 0 plus 1 plus 9 plus 4 plus 0 plus 0 plus 4 plus 4 plus 1 plus 0 plus 1 plus 0 equals 1 4 plus 8 plus 2 equals 2 4. Analysis of variance and company variance 263 FSS2 for total variance equals n array summation minus xijxhiki equals 1, 2, 3, j equals 1, 2, 3, equals 6 to 5 2 plus 7 to 5 2 plus 3 to 5 2 plus 8 to 5 2 plus 5 to 5 2 plus 5 to 5 2 plus 3 to 5 2 plus 7 to 5 2 plus 5 to 5 2 plus 4 to 5 2 plus 3 to 5 2 plus 4 to 5 2 equals 1 plus 4 plus 4 plus 9 plus 0 plus 0 plus 4 plus 4 plus 0 plus 1 plus 4 plus 1 equals 32. Alternatively, it SS for total variance can also be worked out thus. SS for total equals SS between plus SS within equals 8 plus 24 equals 32. We can now set up the ANOVA table for this problem. Table 11.2 Source of variation between sample within sample total SS 824D. F 3 to 1 equals 2 MSF ratio 8 halves equals 4.00 12 to 3 equals 932 12 to 1 equals 11 and 24 ninths equals 2.67 4.00 2.67 equals 1.55% F limit. From the F table F2, 9 equals 4.26. The above table shows that the calculated value of F is 1.5, which is less than the table value of 4.26 at 5% level, with D, F being version 1 equals 2 and version 2 equals 9, and hence could have arisen due to chance. This analysis supports the null hypothesis of no difference as sample means. We may, therefore, conclude that the difference in wheat output due to varieties is insignificant and is just a matter of chance. Solution through shortcut method. In this case, we first take the total of all the individual values of n items and call it as T. T in the given case equals 60 and n equals 12, hence, the correction factor equals T2, n equals 60 times 60 twelfths equals 300. Now total SS. SS between and SS within can be worked out as under. Total equals minus 2 SSXTNIJ 2 BGI equals 1, 2, 3, J equals 1, 2, 3. 264 Research methodology equals 6 2 plus 7 2 plus 3 2 plus 8 2 plus 5 2 plus 5 2 plus 3 2 plus 7 2 plus 5 2 plus 4 2 plus 3 2 plus 4 2 60 60 1 2 times FHGIKJ equals 332 to 300 equals 32 SSTNTNJJ between equals minus DIBG2 2 equals times FHGIKJ plus times FHGIKJ plus times FHGIKJ minus times FHGIKJ 24 24 420 20 416 164 60 60 12 equals 144 plus 100 plus 64 to 300 equals 8 SS within equals minus n array summation XTNIJJJ 22DI equals 332 to 308 equals 24. It may be noted that we get exactly the same result as we had obtained in the case of direct method. From now onwards we can set up a ANOVA table and interpret F ratio in the same manner as we have already done under the direct method. Two-way ANOVA technique is used when the data are classified on the basis of two factors. For example, the agricultural output may be classified on the basis of different varieties of seeds and also on the basis of different varieties of fertilizers used. A business firm may have its sales data classified on the basis of different salesmen and also on the basis of sales in different regions. In a factory, the various units of a product produced during a certain period may be classified on the basis of different varieties of machines used and also on the basis of different grades of labor. Such a two-way design may have repeated measurements of each factor or may not have repeated values. The ANOVA technique is little different in case of repeated measurements where we also compute the interaction variation. We shall now explain the two-way ANOVA technique in the context of both the said designs with the help of examples. A ANOVA technique in context of two-way design when repeated values are not there. As we do not have repeated values, we cannot directly compute the sum of squares within samples as we had done in the case of one-way ANOVA. Therefore, we have to calculate this residual or error variation by subtraction. Once we have calculated just on the same lines as we did in the case of one-way ANOVA, the sum of squares for total variance and for variance between varieties of one treatment is also for variance between varieties of the other treatment. Analysis of variance and company variance 265. The various steps involved are as follows. I. Use the coding device, if the same simplifies the task. E. Take the total of the values of individual items, or their coded values as the case may be, in all the samples and call it TE. Work out the correction factor as under. Correction factor equals TNBG2IV. Find out the square of all the item values, or their coded values as the case may be, one by one, and then take its total. Subtract the correction factor from this total to obtain the sum of squares of deviations for total variance. Symbolically, we can write it as sum of squares of deviations for total variance or total SS22 equals minus XTNBGIJ. V. Take the total of different columns and then obtain the square of each column total and divide such squared values of each column by the number of items in the concerning column and take the total of the result thus obtained. Finally, subtract the correction factor from this total to obtain the sum of squares of deviations for variance between columns or SS between columns. B. Take the total of different rows and then obtain the square of each row total and divide such squared values of each row by the number of items in the corresponding row and take the total of the result thus obtained. Finally, subtract the correction factor from this total to obtain the sum of squares of deviations for variance between rows or SS between rows. The sum of squares of deviations for residual or error variance can be worked out by subtracting the result of the sum of VTH and VTH steps from the result of IVTH steps stated above. In other words, total SS between columns plus SS between rows equals SS for residual or error variance. V degrees of freedom D, F, can be worked out as under. D, F, for total variance equals C, R1 D, F, for variance between columns equals C1 D, F, for variance between rows equals R1 D, F, for residual variance where EC equals number of columns R equals number of rows equals C1 R1 X. ANOVA table can be set up in the usual fashion as shown below. 266 Research Methodology Table 11.3. Analysis of variance table for two-way ANOVA source of sum of squares degrees of mean square F ratio variation SS freedom D, F. MS between columns treatment N area summation minus TNTNJJDIBG22 C1 SSC between columns minus 1 MS between columns residual between rows treatment N area summation minus TNTNIIBGBG22 R1 SSR between rows minus 1 MS between rows residual or error total between columns plus between rows SSSSSS C1 R1 SSCR residual minus 1 total N area summation minus XTNIJ22BG circa R1. In the table C equals number of columns R equals number of rows SS residual equals total SS between columns plus SS between rows. Thus, MS residual or the residual variance provides the basis for the F ratios concerning variation between columns treatment and between rows treatment. MS residual is always due to the fluctuations of sampling, and hence serves as the basis for the significance test. Both the F ratios are compared with their corresponding table values, for given degrees of freedom at a specified level of significance, as usual, and if it is found that the calculated F ratio concerning variation between columns is equal to or greater than its table value, then the difference among columns means is considered significant. Similarly, the F ratio concerning variation between rows can be interpreted. Illustration 2. Set up an analysis of variance table for the following two-way design results. Per acre production data of wheat in metric tons, varieties of seeds ABC, varieties of fertilizers W655X754Y333Z874. Also state whether variety differences are significant at 5% level. Analysis of variance and company variance 267. Solution. As the given problem is a two-way design of experiment without repeated values, we shall adopt all the above stated steps while setting up the ANOVA table as is illustrated on the following page. ANOVA table can be set up for the given problem as shown in Table 11.5. From the set ANOVA table, we find that differences concerning varieties of seeds are insignificant at 5% level as the calculated F ratio of 4 is less than the table value of 5.14, but the variety differences concerning fertilizers are significant as the calculated F ratio of 6 is more than its table value of 4.76. B. ANOVA technique in context of two-way design when repeated values are there. In case of a two-way design with repeated measurements for all of the categories, we can obtain a separate independent measure of inherent or smallest variations. For this measure we can calculate the sum of squares and degrees of freedom in the same way as we had worked out the sum of squares for variance within samples in the case of one-way ANOVA. Total SS between columns and SS between rows can also be worked out as stated above. We then find leftover sums of squares and leftover degrees of freedom, which are used for what is known as interaction variation. Interaction is the measure of interrelationship among the two different classifications. After making all these computations, ANOVA table can be set up for drawing inferences. We illustrate the same with an example. Table 11.4. Computations for two-way ANOVA in a design without repeated values. Step I, Step E, Step E, Step IV, Step B. T equals 60, N equals 12, correction factor equals T and therefore equals times equals BG2, 60, 60, 12, 300 total SS equals 36 plus 25 plus 25 plus 49 plus 25 plus 16 plus 9 plus 9 plus 9 plus 64 plus 49 plus 16, 60 GHF equals 332 to 300 equals 32 SS between columns treatment SS between rows treatment times equals MNL24, 24, 4 plus times 20, 20, 40 times 12 L60 IJK times plus times 16164 equals 144 plus 100 plus 64 to 300 equals MNL 16163 QP minus times plus times 16163 MN 60 60 120 LOPQ times 9 9319193 equals 85.33 plus 85.33 plus 27.00 plus 120.33 300 equals 18 QP minus SS residual or error equals total SS between columns plus SS between rows equals 32, 8 plus 18 equals 6 MN 60, 60, 120 PQ. 268 Research Methodology Table 11.5, the ANOVA table source of variation SSD, F. MSF ratio 5% F limit, or the table's values between columns 8 3 to 1 equals 2 and 8 halves equals 4 and 4 over 1 equals 4 F2, 6 equals 5.14 i.e. between varieties of seeds between rows 18 4 to 1 equals 3 and 18 thirds equals 6 and 6 over 1 equals 6 F3, 6 equals 4.76 i.e. between varieties of fertilizers residual or error 6 3 to 1 times 6 sixths equals 1 4 to 1 equals 6 total 32 3 times 4 1 equals 11 Illustration 3 Set up ANOVA table for the following information relating to 3 drugs testing to judge the effectiveness in reducing blood pressure for 3 different groups of people. Amount of blood pressure reduction in millimeters of mercury. Drug XYZ group of people A1410 11159 11B127 10 11811 C10 11811 Do the drugs act differently? Are the different groups of people affected differently? Is the interaction term significant? Answer the above questions taking a significant level of 5%. Solution. We first make all the required computations as shown below. We can set up ANOVA table shown in Table 11.7 page 269. Analysis of variance and company variance 269 Table 11.6. Computations for two-way ANOVA in design with repeated values. Step I T equals 187, N equals 18, thus, the correction factor equals times equals 187 187 1819 4272. Step E total SS equals 1 4 2 plus 1 5 2 plus 1 2 2 plus 1 1 2 plus 1 0 2 plus 1 1 2 plus 1 0 2 plus 9 2 plus 7 2 plus 8 2 plus 1 1 2 plus 1 1 2 plus 1 1 2 plus 1 1 2 plus 1 0 2 plus 1 1 2 plus 8 2 plus 7 2 187 182 BGLNMMOQPP equals 20191942.72 equals 76.28. Step E SS between columns i.e. between drugs equals times plus LNMOQP minus LNMMOQPP 73 73 656 56 658 58 6187 182 BG equals 888.16 plus 522.66 plus 560.67 1942.72 equals 28.77. Step IV SS between rows i.e. between people equals times LNMOQP minus LNMMOQPP 70 70-659-59-658-58-6187-18 BG equals 816.67 plus 580.16 plus 560.67 1942.72 equals 14.78 Step VSS within samples equals 14 to 14.5 2 plus 15 to 14.5 2 plus 10 to 9.5 2 plus 9 to 9.5 2 plus 11 to 11 2 plus 11 to 11 2 plus 12 to 11.5 2 plus 11 to 11.5 2 plus 7 to 7.5 2 plus 8 to 7.5 2 plus 10 to 10.5 2 plus 11 to 10.5 2 plus 10 to 10.5 2 plus 11 to 10.5 2 plus 11 to 11 2 plus 11 to 11 2 plus 8 to 7.5 2 plus 7 to 7.5 2 equals 3.50 Step VSS for interaction variation equals 76.28 28.77 plus 14.78 plus 3.50 equals 29.23 Table 11.7. The ANOVA table source of variation SSD. F. MSF ratio 5% F limit between columns i.e., between drugs 28.77, 3 to 1 equals 2.28772. 14385 0389. F2, 9 equals 4.26 equals 14.385 equals 36.9 between rows i.e., between people 14.78 3 to 1 equals 2.14782. 7390 0389. F2, 9 equals 4.26 equals 7.390 equals 19.0 counted. Hollow circle hollow circle hollow circle hollow circle hollow circle hollow 270 Research methodology source of variation interaction within samples error total SS 29.23 D. F. 4 3.50 MS 2923 4. F ratio. 73080389 5% F limit F4, 9 equals 3.63 18 to 9 equals 93509. Equals 0.389 76.28 18 to 1 equals 17 asterisk. These figures are leftover figures and have been obtained by subtracting from the column total the total of all other value in the said column. Thus, interaction SS equals 76.28 28.77 plus 14.78 plus 3.50 equals 29.23 and interaction degrees of freedom equals 17 2 plus 2 plus 9 equals 4. The above table shows that all the three F ratios are significant of 5% level, which means that the drugs act differently, different groups of people are affected differently, and the interaction term is significant. In fact, if the interaction term happens to be significant, it is pointless to talk about the differences between various treatments, i.e., differences between drugs or differences between groups of people in the given case. Graphic method of studying interaction in a two-way design. Interaction can be studied in a two-way design with repeated measurements through graphic method also. For such a graph we shall select one of the factors to be used as the x-axis. Then we plot the averages for all the samples on the graph and connect the averages for each variety of the other factor by a distinct mark or a colored line. If the connecting lines do not cross over each other, then the graph indicates that there is no interaction, but if the lines do cross, they indicate definite interaction or interrelation between the two factors. Let us draw such a graph for the data of illustration 3 of this chapter to see whether there is any interaction between the two factors, viz., the drugs and the groups of people. Graph of the averages for amount of blood pressure reduction in millimeters of mercury for different drugs and different groups of people. Y-axis 21 blood pressure reduction in millimeters of mercury 19171513. 11579 groups of people ABCXYZ drugs Fig. 11.1 x-axis asterisk. Alternatively, the graph can be drawn by taking different group of people on x-axis and drawing lines for various drugs through the averages. Analysis of variance and company variance 271. The graph indicates that there is a significant interaction because the different connecting lines for groups of people do cross over each other. We find that A and B are affected very similarly, but C is affected differently. The highest reduction in blood pressure in case of C is with drug Y and the lowest reduction is with drug Z, whereas the highest reduction in blood pressure in case of A and B is with drug X and the lowest reduction is with drug Y. Thus, there is definite interrelation between the drugs and the groups of people, and one cannot make any strong statements about drugs unless he also qualifies his conclusions by stating which group of people he is dealing with. In such a situation, performing F-tests is meaningless. But if the lines do not cross over each other and remain more or less identical, then there is no interaction or the interaction is not considered a significantly large value, in which case the researcher should proceed to test the main effects, drugs and people in the given case, as stated earlier. ANOVA in Latin square design. Latin square design is an experimental design used frequently in agricultural research. In such a design the treatments are so allocated among the plots that no treatment occurs more than once in any one row or any one column. The ANOVA technique in case of Latin square design remains more or less the same as we have already stated in case of a two-way design, excepting the fact that the variance is splitted into four parts as under: I. Variance between columns, E. Variance between rows, E. Variance between varieties, IV. Residual variance. All these above stated variances are worked out as under Table 11.8. Variance between columns or between columns ms22 jtnn array summation minus equals jdibgbgtncss minus equals 1. Variance between rows or ms between rows. Variance between varieties or ms between varieties 22in array summation minus equals tnibgbgbg between columns d f tnrss1 minus equals between rows d f versus tn22n array summation minus equals vbgbgbgtn versus ss1 minus equals residual or error variance or residual ms. Total ss between varieties d f between columns plus between rows plus equals ssc circa ss between varieties minus 1 2 hollow circle hollow circle hollow circle hollow circle hollow circle hollow circle. In place of c we can as well write r or versus, since in Latin square design c equals r equals versus. Conted. 272 Research methodology 2 where total 2 SSXTN equals minus DIBGIJC equals number of columns R equals number of rows V equals number of varieties. Illustration 4 Analyze and interpret the following statistics concerning output of wheat per field obtained as a result of experiment conducted to test 4 varieties of wheat viz. A, B, C and D under a Latin square design. CABDB251919DAA2319 CD20B21D14 C1720B1721 CA20182015 Solution. Using the coding method, we subtract 20 from the figures given in each of the small squares and obtain the coded figures as under: columns 1 1 2 rows 3 CAB minus 1 2 B 5 D minus 1 3 A 3 CDO 4 row totals minus 1 4 AD column totals C minus 3 0 minus 6 Fig. 11.2 Squaring these coded figures in various columns and rows we have 80B1 DBO 4 3 1 1 CA2 0 5 7 2 1 0 7 T equals minus 12. Analysis of variance and company variance 273 Fig. 11.2 B correction factor equals TNBGBGBG2 1212169 equals minus equals SSXTNIJ for total variance equals N array summation minus equals DIBG2 212291113 SSTNTNJJ for variance between columns equals N array summation minus DIBG2 2 equals plus minus RST UVW minus 0 44414749222 BGBGBGBG equals minus 6649775. SS for variance between rows equals minus RST UVW minus TNTNIIBGBGBGBGBG2 22222284341047449 equals minus 2224945. SS for variance between varieties would be worked out as under: column sum of squares 1 2 3 4 CABDBDBCA25119601360199114025291234347465 T equals 122 rows sum of squares of coded figures. 274 Research methodology for finding SS for variance between varieties. We would first rearrange the coded data in the following form. Table 11. 9 varieties of yield in different parts of field. Total TV wheat I23 IVA1 60512B1 3121 C501063 130 Now we can work out SS for variance between varieties as under: SS for variance between varieties equals minus TNTN versus BGBG22 equals minus RST UVW minus 1241464749222 BGBGBGBG equals minus 2304945. Therefore sum of squares for residual variance will work out to 113 7.5 plus 46.5 plus 48.5 equals 10.50 D. F For variance between columns equals C1 equals 4 to 1 equals 3D. F. For variance between rows equals R1 equals 4 to 1 equals 3D. F. For variance between varieties equals V1 equals 4 to 1 equals 3D. F. For total variance equals N1 equals 16 to 1 equals 15D. F. For residual variance equals C1 C2 equals 4 to 1 4 to 2 equals 6. ANOVA table can now be set up as shown below. Table 11. 10. The ANOVA table in Latin square design source of SSD, F. MSF ratio 5% F limit variation between columns 7.50 3750 3250 equals 250,175,143 equals F3 6 equals 4.76 between rows 46 503 4650 31550 equals 1550 175 885 equals F3 6 equals 4.76 con TD. Hollow circle hollow circle hollow circle hollow circle hollow circle hollow circle hollow. Analysis of variance and company variance 275 source of variation between varieties residual or error total SS 48.50 10.50 D, F. 3 mega Siemens. 4853 equals F ratio 1617. 5% F limit. 1617175 equals 6. 1056 equals 175. F3, 6 equals 4.76 113.0015. The above table shows that variance between rows and variance between varieties are significant and not due to chance factor at 5% level of significance, as the calculated values of the said two variances are 8.85 and 9.24 respectively, which are greater than the table value of 4.76. But variance between columns is insignificant and is due to chance because the calculated value of 1.43 is less than the table value of 4.76. Analysis of covariance ANOCOVA y ANOCOVA. The object of experimental design in general happens to be to ensure that the results observed may be attributed to the treatment variable and to no other causal circumstances. For instance, the researcher studying one independent variable, X, may wish to control the influence of some uncontrolled variable, sometimes called the covariate, or the concomitant variables, Z, which is known to be correlated with the dependent variable, Y. Then he should use the technique of analysis of covariance for a valid evaluation of the outcome of the experiment. In psychology and education, primary interest in the analysis of covariance rests in its use as a procedure for the statistical control of an uncontrolled variable. 2. ANOCOVA technique. While applying the ANOCOVA technique, the influence of uncontrolled variable is usually removed by simple linear regression method, and the residual sums of squares are used to provide variance estimates, which in turn are used to make tests of significance. In other words, covariance analysis consists in subtracting from each individual score Y that portion of it Y that is predictable from uncontrolled variable Z, and then computing the usual analysis of variance on the resulting Y, S, of course making the due adjustment to the degrees of freedom because of the fact that estimation using regression method required loss of degrees of freedom. Asterisk 2. George A. Ferguson, Statistical Analysis in Psychology and Education, 4th ed., p. 347. Degrees of freedom associated with adjusted sums of squares will be as under, between K1 with n total n, K1 n2. 276 Research methodology assumptions in ANOCOVA. The ANOCOVA technique requires one to assume that there is some sort of relationship between the dependent variable and the uncontrolled variable. We also assume that this form of relationship is the same in the various treatment groups. Other assumptions are: I. Various treatment groups are selected at random from the population. E. The groups are homogeneous in variability. E. The regression is linear and is same from group to group. The shortcut method for ANOCOVA can be explained by means of an example as shown below. Illustration 5. The following are paired observations for 3 experimental groups. Group 1, Group 2, Group 3 XY 2 1 5 8 3 0 1 5 6 5 2 4 1 2 3 5 1 6 9 7 2 5 1 5 3 2 2 0 1 5 9 1 9 1 8 3 8 2 4 1 2 1 0 3 1 1 9 4 0 3 0. Y is the covariate or concomitant variable. Calculate the adjusted total, within groups and between groups, sums of squares on X, and test the significance of differences between the adjusted means on X by using the appropriate F ratio. Also calculate the adjusted means on X. Solution. We apply the technique of analysis of covariance and work out the related measures as under. Table 11.11 Group 1 Group 2 Group 3 XY 7 2 1 5 8 3 0 1 5 6 5 2 4 1 2 3 5 1 6 9 7 2 5 1 5 3 2 2 0 1 5 9 1 9 1 8 3 8 2 4 1 2 1 0 3 1 1 9 4 0 3 0 total 4 9 3 3 1 1 4 7 2 1 7 5 1 0 5 mean 9.80 6.60 22.80 14.40 35.00 21.00 n area summation equals plus equals x 49,114,175,338. Analysis of variance and company variance 277 correction factor for equals xxn n area summation equals bg 2761627. N area summation equals plus equals y33 72 105 210 correction factor for equals yn n area summation equals bg 22940 n area summation equals x 29476 n area summation equals y 23734 n area summation equals xy 5838 correction factor for equals xyn n area summation dot operator n area summation equals 4732 hence. Total SS for x equals n area summation x2 correction factor for x equals 9476 7616.27 equals 1859.73 SSXX between for equals 49,114,175 correction factor for BG LQ2 22555 plus RST UVW minus equals 480.2 plus 2599.2 plus 6125 7616.27 equals 1588.13 SS within for x equals total SS for x SS between for x equals 1859.73 1588.13 equals 271.60. Similarly we work out the following values in respect of y total SS for y equals n area summation y2 correction factor for y equals 3734 2940 equals 794 SSYY between for equals 3372 105 correction factor for BGLQ2 22555 plus RST UVW minus equals 217.8 plus 1036.8 plus 2205 2940 equals 519.6 SS within for y equals total SS for y SS between for y equals 794 519.6 equals 274.4. Then we work out the following values in respect of both x and y total sum of product of xy equals correction factor for xy equals 58384732 equals 1106 SSXY between for equals 3372 105 correction factor for 4951145 BG plus RSTUVW minus equals 323.4 plus 1641.6 plus 3675 4732 equals 908 SS within for xy equals total sum of product SS between for xy equals 1106 908 equals 198. 278 Research methodology. ANOVA table for x, y and xy can now be set up as shown below. ANOVA table for x, y and xy source D, F. SS for x, SS for y. Sum of product xy between groups 2 1588.13 519.60908 within groups 12 EXX 271.60 EYY 274.40 XE 198 total 14 TXX 1859.73 TYY 794.00 TXE 1106 adjusted total SSTTTXXXYYY equals minus BG2 equals minus 185973 1106 7942. BG equals 1859.73, 1540.60 equals 319.13 adjusted SS within group equals minus EEXXXYYY BG2 equals minus 27160, 198274402. BG equals 271.60, 142.87 equals 128.73 adjusted SS between groups equals adjusted total SS adjusted SS within group equals 319.13 128.73 equals 190.40 ANOVA table for adjusted X source D, F. SSMSF ratio between groups 2190.40 95.28.14 within group 11128.73 11.7 total 13319.13 at 5% level. The table value of F for version 1 equals 2 and version 2 equals 11 is 3.98 and at 1% level the table value of F is 7.21. Both these values are less than the calculated value, i.e., calculated value of 8.14 is greater than table values, and accordingly we infer that F ratio is significant at both levels, which means the difference in group means is significant. Adjusted means on X will be worked out as follows. Regression coefficient for X on Y, i.e., BY equals sum of product within group sum of squares within groups 4. Analysis of variance and company variance 279 equals 198 27440 07216. Deviation of initial group means from final means of groups in X unadjusted general mean equals 14, in case of Y group 1 7.409.80 group 2 0.40 22.80 group 3 7.00 35.00 adjusted means of groups in X equals final mean B deviation of initial mean from general mean in case of Y, hence adjusted mean for group 1 equals 9.80, 0.7216 minus 7.4 equals 15.14 adjusted mean for group 2 equals 22.80, 0.7216, 0.40 equals 22.51 adjusted mean for group 3 equals 35.00, 0.7216, 7.00 equals 29.95 Questions 1.